Hello and welcome to NPTEL MOOC on Applied Electromagnetics. In this module we will discuss wave reflection and transmission in the scenario what is called as the normal incidence from one medium to another medium. In the previous module when discussing skin effect, whether it was on the flat conducting material or the region, or whether it was a round wire, we had seen that one of the ways to excite the surface currents on an imperfect conductor was to actually let a plane wave be incident on that one. In the previous model I showed you a picture where the region below this was all a conductor and the electric field actually had an X component in this way. So, the electric field was in this way. This was caused by some way, if we can actually take a plane wave and then make it fall on the imperfect conductor, these electric field lines will therefore generate a corresponding surface current, and we have seen what happens when there is a surface current at the surface between yesterday in the case we considered was between air and an imperfect conductor. So, these surface currents will then eventually, as they propagate down, they will attenuate and generate they will attenuate and lead to what is called as the skin effect. In this problem that we discussed in the previous lectures, we never really bothered as to what happens to the fields in the incident medium. We call this as the incident medium and this as the second medium. So, this wave was supposed to be incident from the first medium onto the second medium, and we know what happens to this wave in an imperfect conductor as it propagates down, it simply gets attenuated. But what happens to the fields in the first region, that we have not investigated, and that is precisely what we want to do in this case. Okay. We also consider, because we have already analyzed the imperfect conducting case or imperfect conductor or a good conductor case, we will now assume a perfect conducting material. So, for all z greater than 0, right. So, z equal to 0 is the interface plane that separates the interface between air and a perfect conductor, and by perfect conductor we mean its sigma equal to infinity. Okay. So, in that case, and assuming in the region 1 is an insulator, we can have for example air as an insulator with its impedance of 377 ohms, or in general you will have a certain value of mu naught and an epsilon. I am assuming that the first medium or the first region where the plane wave is travelling is also non-magnetic, and therefore mu is equal to mu naught. Okay. So, this is the problem that we are looking at today. You have an electric field incident and a magnetic field incident. Together of course EI and HI form an electromagnetic wave. So, this is a uniform plane wave which is propagating along z direction. It is propagating along z axis, and the propagation coefficient is given by beta I. Remember what beta I is? Beta I is omega square root mu 0 epsilon if the medium is in general insulator, or it would be equal to omega into square root mu naught epsilon naught if we are talking about air. Okay. And of course 1 by square root of mu naught epsilon naught is equal to the speed of light, or we will call this as up1, where up denotes the phase velocity and that 1 denotes that we are in the region 1. Okay. So, this is the region 1 which is insulator, region 2 is a perfect conductor with the value of conductivity being equal to infinity. So, now this wave is propagating from z equal to minus infinity, and then it approaches the z equal to 0 interface. This is the z equal to 0 interface, okay, and the vertical axis is along the x and y axis will be coming out of this particular plane. So, this is how the y axis would be coming out. Okay. So, that is what we have. What happens to this uniform plane wave as it impinges on the good conductor? Okay. In order to answer that, we need to know what is the boundary condition that is necessary that these fields have to satisfy. Okay. What is the boundary condition between a perfect insulator such as air and a perfect conductor? So, with the conductivity going all the way to infinity, what is the boundary condition? Well, the total tangential electric field, okay, must be equal to 0, right. So, you have ET1 being the tangential electric field there, that one must be equal to 0, and the tangential magnetic field must be equal to the surface current density or the sheet current density that needs to be there. Clearly in a perfect conductor there cannot be a ET2, that is tangential component of the electric field, nor you will have the magnetic field component. So, these boundary conditions must be satisfied. But our problem is not the static problem, okay, because our electric field EI, if you write it in the complete vector notation, will have some amplitude. Let us call this as x hat E1, okay, and it is propagating along the z axis. So, you have e to the power j omega t minus beta I into z. What is omega here? Omega is the frequency of the plane wave, okay. So, omega is the frequency of the plane wave and beta I is related to that particular frequency by the expression that we have written. Similarly, the magnetic field for the incident wave will be along the y direction, because the wave is actually propagating along the z axis. E cross h must point in the direction of the propagation, which is z, and the amplitude here will of course be E1 divided by eta 1, where eta 1 is the medium impedance given by square root of mu naught divided by epsilon naught for air, or it is in general given by mu naught divided by epsilon 0 or epsilon r. The product of epsilon 0 and epsilon r is what we normally call as epsilon, okay. So, this is the medium impedance, and it also has the same time and space dependence as does the z component, okay. Now, if this is all that is incident, okay, now at z equal to 0 is the incident plane of interface, which actually separates the insulator and conducting materials, right. So, all this region is conductor, all this region is an insulator. So, at z equal to 0, if I try to apply the boundary condition, what will that boundary condition tell me for EI? It will tell me that x hat E1, or rather x hat I can drop, because x hat indicates that to the medium the electric field is tangential, and in this case it is tangential, right. So, if this is the medium, so you can look at this one, if this is the medium and the wave is propagating with the electric field along my thumb direction, and once it hits this one here, right. So, once this hits the interface, which is this hand, right, then the electric field amplitude at z equal to 0, this my hand is z equal to 0, the electric field, because it is tangential, see this thumb is tangential to this interface, right. So, because of that, the boundary condition tells me that this tangential electric field must vanish. Now, how can the tangential field vanish for all values of time? It is one thing that it can vanish at a particular time, but the boundary condition is not dependent on the time, it is independent of time. For all times the tangential electric field must vanish, and the magnetic field, which is this finger, let us say, okay, such that x cross y will be along the z axis, the magnetic field H will have to generate a sheet current, a surface current on this interface. So, to the left of this hand is the air, and to the right of this hand is the conducting material, and this one separates the air and the conducting medium, and therefore forms the boundary. So, clearly if I just have the incident wave or the incident electric field and the incident H field, I cannot satisfy boundary condition for all time, correct, because evaluate this one at z equal to 0, what do you get? The tangential electric field in the region 1 will be E1 e to the power j omega t, okay, or you can say that this is E1 cos omega t, because fields have to be real, okay. And this, if it is equal to 0, because there is no ET2 here, there is no tangential component of the transmitted field, there is nothing to be transmitted on the second region. So, we have the condition that says that E1 cos omega t equal to 0, and if this has to hold for all values of t, then there is only one trivial solution which makes E1 equal to 0. Obviously, that is not what we want, right. So, with only incident waves you do not satisfy boundary conditions. So, what should happen then if you want to satisfy boundary condition? Well, you will have to have a reflected wave at this point, okay. So, you will have a reflected field, this reflected field must propagate along minus z direction, because of course the incident wave is propagating along plus z direction, this wave must propagate along minus z direction, okay. So, let me tentatively write the reflected electric field corresponding to the reflected uniform plane wave as having the same direction as the incident wave. So, x hat, and instead we will write this one as E1 minus. Okay. So, minus indicates that this is a reflected wave amplitude. Okay. So, let me also go back and adjust the amplitudes for incident fields. I will write them as E1 plus and E1 plus, so that I know plus indicates the wave propagating along the plus z direction and a minus indicates a wave propagating along the minus z direction. So, what will be the frequency of the reflected wave? Well, because you can show by the application of the boundary condition that suppose you postulate that this will have a different frequency, let us say. Okay, I will just show you that one. So, you have e to the power j omega prime t minus beta r z. Okay, beta r is the reflected field. So, in this region now you have a reflected field which is propagating along the minus z direction. So, this is the reflected field ER component and the propagation is along the direction along minus z direction. Okay. And the magnetic field of course will have to have a minus y direction. Why should I have a minus y? Because x cross y will give you the z direction of propagation, whereas x cross minus y will give you a minus z direction of propagation, which is exactly the direction in which the reflected wave is propagating. Therefore, the reflected magnetic field HR will be along minus y direction, and then it will have E1 minus divided by eta 1 e to the power j omega prime t. This should be plus beta rz because the wave is propagating along minus z direction. Okay. So, these are the fields that I have written. The question is, can omega be different from omega prime, and what will be the relationship between beta I, because beta I is the magnitude of the incident wave vector and beta r is the magnitude of the incident wave vector or the propagation constant, right. So, what should be the relationship between the two? In region 1, which is where the action is now taking place because nothing is propagating inside the second medium. So, in medium 1 where the action is taking place, the total tangential electric field, okay, will be the sum of incident and reflected fields, right, evaluated at z equal to 0. So, in the z equal to 0 interface, the total tangential field, let me write this as E total, will be equal to x hat E1 plus e to the power j omega t plus x hat E1 minus e to the power j omega prime t, and this total electric field must then be equal to 0. Why should it be equal to 0? Well, boundary conditions tells you that this must be equal to 0. Then you have a relation which now tells you E1 plus e power j omega t must be equal to minus E1 minus e power j omega prime t. So, on the left hand you have a sinusoidal wave. If you take the real part of it, on the left hand you have a real cosine wave, on the right hand side also you have a cosine wave, and these two frequencies, if they are different, then their amplitudes will be equal only at a few points in time. Okay. But you want this relation to hold for all values of time. So, clearly if that has to happen, the frequencies on the left hand side of this expression must be equal to the frequency on the right hand side of this expression. Okay. Therefore, omega prime must be equal to omega. So, the reflected wave will have the same frequency as the incident wave. Okay. So, the only conclusion now that I have left is to tell you that E1 minus, which is the reflected wave electric field amplitude, must be equal to minus E1 plus. Okay. So, E1 minus is equal to minus E1 plus. Therefore, I can go back and rewrite the total electric field as x hat, E1 plus is common, e to the power j omega t is also the same because the frequencies are the same. So, you have e power minus j beta I z minus e power minus j plus j beta r z. Now, what about beta I and beta r? Should they be different or should they be equal? Look at what is beta I. Beta I depends only on the frequency omega, and we have shown that the reflected fields or the reflected wave also has the same frequency omega and square root of mu epsilon or mu naught epsilon naught, because we are considering air in this example. So, none of this actually depend on the direction, right. The propagation constant, the magnitude of the propagation constant depends only on the frequency and on the constituent parameters mu naught and epsilon naught of the medium, right. Clearly this must also be the case for beta r, because beta r corresponds to the propagation coefficient of a wave which is propagating in the same medium as the incident wave. Its beta r magnitude must also be equal to omega square root of mu naught epsilon naught. So, beta r is equal to beta I. Okay. Because beta r is equal to beta I can replace this r subscript here with I, and what is this expression in here? Exponential of e power minus jx minus e power jx is actually minus 2j sin x, correct? This is a sin x expression and 2j gets multiplied out there. Therefore, the total electric field in the region 1, which is now the sum of incident and reflected waves, is given by, it of course has the same direction as x, but this is given by E1 plus, we will write this as minus 2j, okay, sin beta I z, right. So, beta I is equal to beta r, therefore, it does not matter whether I use beta I z or beta r z. Okay. I have not written the complex exponential factor e power j omega t because I want to write only the phasor form of these expressions. Therefore, I have simply dropped e power j omega t. I can drop it. Please remember, I could not have dropped that one in these expressions because I am assuming that they are different. So, two phase, I mean when I talk of a phasor, when I sum the phasor components, they all have to have the same frequency. So, because of this condition that we have proved, I am able to remove the e power j omega t factor from this expression, and whatever that I am left out is the phasor of the total electric field. So, you have a phasor electric field over here, which we have shown that should be equal to minus 2j sin beta I into z. I will leave the exercise, I will leave this as an exercise for you to find out what will happen to the total magnetic field. Of course, on the surface the magnetic field will have to be such that the sum of the incident amplitude and the reflected amplitude must be equal to the total surface current out there, but away from the interface what happens. So, on the interface at z equal to 0, I know that Hi plus Hr must be equal to the total surface current Js, but far away from the interface what should be the total magnetic field, right. I will leave this as an exercise for you to find out what should happen to this one, and you will probably not be surprised, but you will see an appearance of cos beta I into z somewhere over there. I will leave this as an exercise for you to find. Alright, now we have looked at the fields that are present at the region in region 1 away from the interface. Do these equations surprise us? Fortunately, these equations are not surprising to us because very similar thing happened in one of the earlier modules when we talked of short circuit termination of a uniform lossless transmission line. So, you had a lossless transmission line wherein you had an incident wave, but then when you terminate that transmission line with a short circuit, what happened? There was a reflected voltage or a reflected current, and the reflected voltage amplitude was minus the incident voltage, right. So, VR is equal to minus Vi. In other words, with a short circuited termination, the reflection coefficient that you obtained was equal to minus 1, right. So, that happened earlier, and we know that the fields actually formed a standing wave, and in this case there is no difference. The fields do form a standing wave because the incident wave is coming in, the reflected wave is going back at the same time, but with a phase of 180 degree opposite with respect to the incident wave. They both will interfere together to form a standing wave pattern. In fact, if in this particular case the standing wave pattern will be the maximum because the reflection coefficient will actually be equal to minus 1, right. The magnitude of the reflection coefficient is equal to unity in this case. So, what is our lesson? We can in fact think of this space problem. So, you had a air, right, you had air with the impedance of eta 1, and you had a conductor, and we found that for a perfect conductor where sigma tends off to infinity, right, whatever the incident electric field, that incident electric field was completely reflected, correct, with a reflection coefficient of minus 1. So, because of this reflection coefficient being minus 1, this conductor is equivalent to a short circuit termination. So, this is a short circuit termination of a uniform lossless transmission line whose characteristic impedance Z0 was equal to eta 1. So, the medium 1, which is air, can be considered as a uniform lossless transmission line, and then terminated, when you consider a perfect conductor, terminated by at its load, or you can consider the conducting material as its load, and the impedance of that conducting material, perfect conducting material, is a short circuit. Now, does it also make sense? Yes, we have already seen that the impedance of a conducting material, right, is complex, and it is given by j omega mu divided by sigma under root. So, we have seen this one earlier. Of course, there is a plus j omega epsilon term, but we neglect this plus j omega epsilon term, assuming that this is a good conductor. But now we are not even talking of a good conductor, we are talking of a perfect conductor. For a perfect conductor, sigma goes off to infinity, and therefore eta goes off to 0. So, eta of a perfect conductor, the impedance of the perfect conductor goes to 0. Of course, this also is true because the electric field in a perfect conductor goes to 0. So, you do not have any tangential electric field, and therefore, because of that reason, this electric field also goes to 0. The impedance of a perfect conductor is a short circuit. So, whenever you terminate this one, you do obtain a short circuited kind of a equivalent circuit of a transmission line. So, the problem that we had in terms of waves can be rewritten in terms of the transmission line problem. Okay. Now, let us very quickly jump to another scenario where I have a second medium of impedance eta 2, the first medium having an impedance of eta 1, which means I am assuming that this is also insulator. Again, I will assume that this is a perfect insulator, so which means that sigma will be equal to 0. The same condition of sigma equal to 0 is true even in the region 1. Okay, so, this is region 1 and this is region 2. As before, I have an incident electric field which will have an amplitude of E1 plus, okay, propagating along the z axis. This would be my z axis as before. This vertical line is along the x axis, and y axis will be coming out of this plane. Okay. So, I have the magnetic field which has an amplitude of H1 plus and is along the y axis. Of course, H1 plus is nothing but E1 plus divided by eta 1. Okay. We know in this case that there has to be reflected field, otherwise you will not be able to satisfy the boundary conditions. Okay. You can show that by trying to assume that when there is an E1 plus and H1 plus, there would of course be some waves which are transmitted into the second medium as well, right. So, the second medium wave is also travelling along the plus z direction, and the amplitude of this second transmitted field can be written as E2 plus. The subscript 2 indicates that this is a region 2. Okay. And there will be a magnetic field, we will not, magnetic field in the same direction, because electric field we have assumed to be is in the same direction for incident and transmitted fields. So, this would be H2 plus. Of course, H2 plus will be equal to E2 plus divided by eta 2. You can show by applying the boundary condition that only E1 plus cannot be equal to E2 plus, right, because the values of eta 1 is usually different from the values of eta 2, otherwise there is no boundary that we are actually talking about. Because this is not equal, there has to be some reflected field, right. There cannot be additional transmitted fields, you can show that, because it only means that you can try to increase this one, but please remember these have to be valid for all all times and at all points along the z equal to 0 plane. Okay. Because of that, you can clearly show that there has to be a reflected wave, and that reflected will be at the same frequency as the incident wave. The transmitted wave will also be at the same frequency as the incident wave. Okay. And what would be the reflected field looking like? The reflected field we will assume that it will be in the same direction as the incident field, the electric field of that one. So, you have an amplitude of E1 minus for the reflected, and it is propagating along minus z direction, and the magnetic field will have a minus y direction, so as to conform to the fact that the reflected wave is propagating along the minus z direction. Okay. Now, applying the total electric field, the tangential electric field boundary condition at z equal to 0, I am not going to invoke e power j omega t, obviously, because we are assuming that they are all phasors, and it is true they are all phasors in this case, all the frequencies are same, the incident, reflected and transmitted. Okay. So, in the region 1, the total tangential electric field has an amplitude of E1 plus E1 minus, that must be equal to the tangential electric field in the region 2, which is E2 plus, correct. What will happen to the magnetic field? Well, magnetic field amplitudes H1 plus H1 minus, okay. I have not yet written them in terms of electric field here. So, this must be equal to H2 plus, okay. So you might ask what happened to the surface current density. Well, we do not have any surface current density because this is the interface between two insulating materials. So, no surface current density, and replacing H1 plus and H1 minus as well as H2 plus with respectively with appropriate values of E1 plus by eta 1, E1 minus by eta 1, and the direction of the magnetic field is of course along the minus y direction, therefore there will be a minus sign here, and then you have E2 plus divided by eta 2. Please remember that H will be E2 plus divided by, or H will be E by the medium impedance eta 2. Now what is that we have? We have a simple matrix equation. So that will have a matrix elements of 1 by 1 1 1 by eta 1 1 by eta 1 times E1 plus E1 minus must be equal to 1 1 by eta 2 times E2 plus, okay. So I have this simple equation. Now it is only a matter of calculation, little bit of an algebra for me to define what will be the ratios of E1 minus to E1 plus. This ratio of E1 minus to E1 plus of course is what is called as the reflection coefficient, and the ratio of E2 plus to E1 plus, E2 plus is the amplitude of the transmitted field to E1 plus which is the amplitude of the incident field, this ratio will be called as a transmission coefficient, right. I will leave this as again a small exercise for you. You just have to sum and then difference the equations on the left and the right hand side to show that the reflection coefficient for the electric field in this particular case, okay. If you want you can put a subscript of electric field E here, but I am not going to do that. This gamma, which is the ratio of the reflected field amplitude to the incident field amplitude, is given by eta 2 minus eta 1 divided by eta 2 plus eta 1. And similarly you can show that the transmission coefficient, which would be the ratio of E2 plus divided by E1 plus, this is the incident, this is the transmitted, this would be equal to 2 eta 2 divided by eta 2 plus eta 1. In fact, this medium that you had eta 1 and eta 2 can be considered to be a transmission line, okay, with the load, the second medium acting as the load with an impedance of eta 2, and the first medium being a uniform transmission line having a characteristic impedance of eta 1, okay. So at z equal to 0, which is where the interface is separating the two medium, the problem of the waves can be quite easily in an analogy shown to be equal or equivalent to the problems of a transmission line, okay. So we will have more to say about this in the next module. Until then, thank you very much.